So there are four types of macromolecules. We've been talking about all this energy. We've been talking about the formation of larger molecules from smaller energy poor ones by what type of reaction? Dehydration synthesis, right? We're going to form larger molecules, and that's the role of the human body, to take in energy, right, in whatever form we can get it in, store it away, and then use it when we need it. So to store it away, we're going to use dehydration synthesis, and we're going to build these larger molecules. These are collectively known as macromolecules, and there are four types in the human body. Macromolecules fall under, or types of macromolecules are carbohydrates, lipids, proteins, and nucleotides or nucleic acids. We'll be talking about all these here in the next set of three or four lectures. And we need to understand that when we start talking about the first group, carbohydrates, there are many characteristics that are appropriate and describe them, and they provide the most energy that we're going to need in the form of sugars, starches, many other types of forms that we use to get energy from. We will see that their ratio, remember the three important elements for carbs or for organic compounds are carbon, hydrogen, and oxygen, and they will typically be in a ratio of 1 to 2 to 1. The most common one that you'll get really familiar with over the course of A&P 1 and 2 is glucose. And glucose is a 6-carbon molecule. It turns out it has 6 carbons, 12 hydrogens, and 6 oxygens in a 1 to 2 to 1 ratio. Now, some carbs are used to store energy away. Some carbs are utilized immediately. We're going to see that there are three major groups of carbohydrates. Monosaccharides, or single sugar units. Single saccharide is the monomer, or the sugar unit of a carbohydrate. Disaccharides and polysaccharides. Okay, so the first group here is the monosaccharide. We see there are many examples. Those that are 5 carbon groups large are called pentoses. That's not necessarily important, but the sugar known as ribose and deoxyribose that help to form our nucleic acids will be found here. And then we have our 6 carbon group, which has glucose, which we just mentioned, fructose, the sweetest of all carbohydrates, a 6-carbon sugar. In fact, has the same chemical formula as glucose, C6H12O6, but there's obviously a different arrangement and some different compounds found here. You notice they're ringed carbon compounds, just a little different than what we've been seeing. And then galactose, which is also an important carbohydrate. So glucose has many structures and is very, very critical to your understanding of how we accomplish metabolism in the human body. We can represent it in many ways. There's the structural formula with the 6 carbon compounds in a nice straight chain. But the more common way to represent it is in the ringed formula. You also see the ball formula, the model formula, if you will, showing you the arrangement of carbons, oxygens, and hydrogens in glucose. Glucose is the singular most important metabolic compound we will ever talk about in anatomy and physiology. So those are the monosaccharides. Disaccharides are formed by combining 2 monosaccharides in what type of reaction? Dehydration synthesis or condensation, correct? So we're going to put to form, in this particular example, sucrose, which is commonly known as table sugar, right? And so we take a glucose molecule and a fructose molecule. They both have OH groups coming off one of their carbon compounds. The OH from one and a hydrogen from the other will combine to form water. You'll notice it on the right side of the equation. It's one of the products. And so by putting glucose and fructose together, by supplying some needed activation energy, we will combine those together to form sucrose. or common table sugar. Some other common disaccharides are maltose, where we put together two glucose molecules. You'll commonly see those with grain sugars or in cereal. And lactose, that I'm sure you know about, is milk sugar. Glucose and galactose combined together in this particular molecule. The third type of carbohydrates besides monosaccharides and disaccharides are polysaccharides. So polysaccharides are the storage form of carbohydrates. When we need to put energy away, when we've consumed plenty, then what we'll do is put it away as a polysaccharide. Polysaccharides, the ones that are listed here, are nothing more than conglomerations, groupings of glucose molecules. We have glycogen, that's the animal storage form of glucose, starch, and cellulose that are found in plants. This is the way they store away energy, typically mostly starch, but cellulose is found in cell walls and is certainly an appropriate means of storing away excess glucose. So if they're all storage forms of glucose, what's different about them? Why are we considering them why do we label them as three different compounds? More importantly, can we digest each of them the same way and with the same efficiency? And the answer is no. Glycogen is the way we store carbohydrates away, in particular, of course, glucose. So we're talking glucose here. Glucose is a 6-carbon compound. We're going to represent it with a hexagon here. And I'm also going to teach you a little shorthand that's commonly used in organic chemistry. At each one of these little bins right here, we have a carbon molecule, but it's not typically drawn. It's understood that if there is a bin there, and that implies it's a carbon if there's nothing listed. If there was an oxygen there, I would put an oxygen present because that is something different. Otherwise, it would be assumed that there's a carbon there. Now, you know also that carbon has to form 4 bonds, yet if we look at this particular aspect right here where there's a carbon, why are there only 2 bonds, right? This one this way and this one this way. Well, there are really 4 bonds. We just don't draw them because it typically will clutter up the map. There are what will be assumed to be hydrogens, unless we draw something different. This will also apply to straight chain molecules. We'll see carbons. We'll typically only draw the carbon molecules in these long straight chains, okay? And we won't draw the other accompanying hydrogen molecules, if you will. All right, so we should draw those out there, but because it becomes rather onerous, we don't. So we keep this as shorthand in organic molecules. If you don't see anything hanging off the carbons, it's well understood they'll have 4 bonds, that those are hydrogens. If it's something different, we will make a point of putting that different atom. Same thing for the ring molecules. So with glycogen, we're going to have several of these rings that are going to be hooked together, these glucose rings, right? And in glycogen, excuse me, what we'll have is several side rings and chains of these rings coming off, right? And so you'll have several of these coming off. And so what this means is that when we break this molecule down, we are going to see that the molecules that are breaking it down are only going to attack at the ends, right? They'll attack at the ends of these chains. And the molecules that we're using to break down this glycogen are called enzymes. And these enzymes only attack at the ends of the chains. And glycogen has a bunch of these ends, right? It has several of them. And so there's lots of places for the enzymes to be attacking. The bonds are easily recognized by the enzymes, and they just break it down really easily. Starch, we can digest it, but it gives us a little more of a problem because the starch molecule has slightly different bonds between the glucoses, and also fewer of these side sprouts, if you will, these side chains of glucoses. So there's fewer places for the enzymes to attack. They can only attack again at the ends. They don't attack in the middle, right, and begin breaking it down, only at the ends. So we're okay with starch, but we're not as efficient as we are with glycogen. Cellulose, on the other hand, takes things to extreme here, and we have no side chains pretty much. In addition, the bonds that link the glucoses together are different as well. They're not the conventional ones we have in our own bodies. So we can't digest cellulose because of that. Zero, no way. How do you know? Because whenever you eat anything with a cell wall in it, you do a very, very bad job of digesting it. Think corn. Corn ends up, eat it one day, you see it the next, right? So we can't digest cellulose. We do pretty good with starch and really good with glycogen because that's the molecule we make.